Good morning, everyone. My name is Nick May. I do marketing here at LSP Technologies. My pleasure to introduce Joana Antunes, who is currently pursuing an engineering doctorate in sustainable materials and manufacturing with the universities of Cranfield, Warwick, and Exeter. Please welcome Joana Antunes.
Well, thank you very much. Hello, everyone, or good morning, and good afternoon, or good evening, depending on where you are in the world. Thank you very much for coming to listen to this presentation. And I'd also like to thank the organizers, obviously, for allowing me with the opportunity to share my work in this event. My name is Joana. I am currently pursuing what here in the UK we call an engineering doctorate, or an NGD, which is essentially an engineering PhD with some more of an industrial focus and MBA taught modules. And as Nick said, this is part of the Centre for Doctoral Training in Sustainable Materials and Manufacturing. And it's a collaboration between the universities of Cranfield, Warwick, and Exeter, all here in the UK. So as you can see by the title, the presentation today will be about treating friction stir welded structures using laser peening. In this particular project, I'm aiming to treat friction stir welded 2024 aluminium sheet material. And there are three main research objectives that I'm trying to accomplish. The first one is to demonstrate how fatigue and static behavior can be improved for this friction stir welded alloy using the laser shot peening treatment. Secondly, is to understand what are the underlying processes that may be causing these improvements. And thirdly, but not less important, I'll have to find a way of coping with the tensile residual stresses that will also be generated, since those could potentially be detrimental to the fatigue life. So for those who may not be familiar with friction stir welding, this technology is what we call a solid state joining process. So there's technically no fusion. And this has plenty of advantages when we compare it to other welding processes. Not only it produces less distortion and it's very efficient, but one of the main advantages is that it needs no filler material, which is obviously very good news for any industry where weight is an important constraint. However, this process has a few challenges that need to be overcome before industry implementation. So in all welding process, basically, that aim to join high-strength aluminium alloys, friction stir welding is also prone to a distribution of defects, tensile residual stresses, and softened heat-affected zones. So the softened heat-affected zones mean that different regions of the welds will have different mechanical properties compared to the base material. And you can see that in this plot at the bottom, where the stress and strain curves were obtained using DIC, or digital image correlation. And as you can see, there is about a difference of about 30 megapascal when we compare the base material to these different weld regions. So essentially, the combination of softened zones, defects, and tensile residual stresses has been proven to reduce the fatigue strength and life when compared to the parent material. As I explained in the previous slides, there is technically no fusion in this process. However, the heat input is high enough to leave the material with substantial residual stresses. So I measure these stresses, or better, I measure the strains and calculated the stresses in my fatigue samples, which you can see here at the top, using what's called the incremental central hole drilling methods by placing a rosette gauge in the center of the weld. And as you can observe, the stresses along the weld line, which are the red dots, are tensile in nature and close to 100 megapascal. However, for this particular project, the transverse direction of the welds is the most relevant because it coincides with the loading direction of the fatigue specimens that I'm using. So luckily, these stresses are almost negligible, as you can see in blue. And this is due to the fact that the variation in temperature in this direction is very small when you compare it to the longitudinal direction, which is also the traveling direction of the tool. So now that we understand the challenges that are associated with friction stir welding, I'll show you the work that I have been developing, trying to understand how these joints behave under fatigue loading. And keep in mind, there will be an interaction between the stresses that are being applied, the residual stresses that come from the friction stir welding process, and the residual stresses that will come from the peening treatment. So in order to study this, I performed some fatigue tests using an R ratio of 0.1 and a test frequency of 5 Hz. And as you can see in this test matrix, I tested 5 different sample conditions. So I have samples without any weld, so that's just the pristine aluminium material, which I'm calling reference. Then samples in what we call as welded condition, so samples presumably without any defects. And finally, samples with 2 different defect depths, 200 and 400 micrometer. And these are what we call lack of penetration defects, which form when there is an incomplete bonding of the 2 plates. So if you think that we're trying to join these 2 plates of aluminium, the tool will be on the top rotating, and that side is called the shoulder side, and the opposite side is the root side, which you can see in these pictures. So the lack of penetration defect will be on the root side if there's incomplete bonding of these 2 plates. So here you can see the difference between the pristine aluminium material with no weld, which is the reference in black, and samples that were friction stir welded without any defects, presumably, and which I'm calling as welded and are in red. And please be reminded that this is before any peening treatment yet. So we can conclude that by using friction stir welding, we're reducing the life for about 70% when we compare it to just the pristine aluminium material. And this is obviously due to the challenges that I talked about earlier, mainly the softening effect happening at the joints, as well as the residual stresses that are involved in the process. Things start to get a bit more interesting when we consider these lack of penetration defects. So as you can see in blue triangles, when the welds have a defect that is only 200 micrometer deep, there's no difference in fatigue life when we compare it to the as welded samples with no defects, which you can see in red. And this is, of course, within the typical scatter that you would see in fatigue tests. On the other hand, if the defect is 400 micrometer deep, which you can see in green, there is a reduction of about 80% in fatigue life, which is quite substantial. So what this is telling us is that the 400 micrometer defect is clearly acting as a crack initiation site, while the 200 micrometer defect, the stress intensity factor at the defect tip is not dominant when we compare it to the effects of the microstructural and residual stresses on the shoulder side, which is typically the failure location. So a very interesting finding was when I observed the fracture surfaces using SEM or scanning electron microscopy. And I saw that the cracks on those 400 micrometer defects did not initiate where the depth of the defect was the highest. So this is telling me that the geometry of the defect, said how sharp or how blunt the defect may be, is having a predominant effect on the failure of the joint. So failure is influenced not only by the depth of the defect, but after a certain critical depth, it's the geometry of the defect who's playing the dominant role. And this is something that we'll be studying further in the future for this project. So in order to try to improve the life of these joints and prevent crack initiation from this lack of penetration defects that I just showed, the main objective of this project, as I told you in the beginning, is to understand if laser shot peening could have a beneficial effect on this type of joint. So Cranfield University has been involved in other projects where laser peening was used to treat aluminium sheet material, more specifically with scratch damage done to the material. And those results were very promising at the time. So the hypothesis here is that laser peening could potentially have a similar beneficial effect in the friction stir welded aluminium. However, peening over thin plates or sheet material, as we call it, is not straightforward at all. So the reduced thickness of the plate involves many challenges to the process, such as back surface wave reflection and the fact that there's less material available for the elastic constraint. So this makes it very challenging to achieve the desired residual stress fields that we are looking for in this project. So if you look at the figure on your right, you can see how I would like the residual stress fields to look like. And the objective is to get compressive stresses about 0.5 millimeter deep into the surface. So the compressive stresses can cover any lack of penetration defects. And the magnitudes of that compressive stress should be as high as possible. However, it's also important to try to minimize the balancing tensile stresses that will also be formed, or at least trying to keep them away from any potential critical locations or defects. So in order to try to achieve that target residual stress profile, I conducted an optimization of the laser parameters for quite some time. And this was the end result using the parameters that you can see on the right. And this was done using double-sided peening. So both sides of the specimens were peened, the shoulder sides and the root sides. And as you can see, I was able to obtain a peak compressive stress of about 170 megapascal compressive on both sides, which is quite good for this thickness, which is 2.3. And the surface stress is also compressive, which is important to try to prevent crack initiation from the irregular surface that is characteristic of the friction stir weld. And the peak tensile stress, was about 100 megapascal, which is quite significant. However, the good news is that that stress is on a non-critical location, basically away from these potential lack of penetration defects. So finally, it's our fatigue test results after peening with the parameters that I showed you for as welded samples with no defects. So you can observe that there is a live improvement about a factor of 2, but for the lower load range that I tested. You may be surprised about the lack of improvement for the higher side of the spectrum. However, you can see that the stresses are quite high, about 350 megapascal, which is significantly high when we compare it to the compressive stress that we were able to achieve with the peening treatment. So I can conclude that these results are actually quite satisfactory for the lower and, to be fair, the more realistic part of the load spectrum. So you can see this is clearly work in progress. I'm currently in the process of testing the rest of the as welded samples and also to test the samples with the defects. So I'm not able to show you today all the results for the peen samples. So instead, I'm going to show you some other research strands that I have also been working on for this project, which consists in developing an FE module to try to optimize the residual stress fields in friction stir welding. So essentially here, I am investigating what is the ideal residual stress profile that I need to achieve with the laser peening in order to try to optimize the fatigue life of welded samples, of friction stir welded samples containing lack of penetration defects. So I'm doing that by calculating the delta K effective at the defect tip and comparing that to the delta K threshold. So the assumption here is that if the delta K effective is smaller than the delta K threshold for this alloy, then it means there will be no crack initiation, presumably. So this is the geometry of my fatigue samples that I recreated in Abacus. I need you to understand that I'm modeling just a quarter of the sample to make it more simple. So you can see that you need to think about a cut section through the thickness, which is cut AA, and which you can see in the picture, and then another cut in the center for symmetry. This is why it makes it a quarter. You can see that I'm placing a notch in the sample to try to recreate a lack of penetration defect, but this is obviously not to scale. So the depth of the defect is going to be around 400 micrometer deep, while the thickness is only 2.3. So that's not to scale at all. So a crucial step for these FE module developments was to create an iterative algorithm to introduce the desired residual stress fields into the FE module. So this was needed because when you try to apply a predefined residual stress fields into an Abacus model using a subroutine called Cigini, Abacus tries to rebalance the stress fields because the FE code is trying to find the equilibrium condition. So this will result in stresses in the end that are different from the target stress that I was trying to apply. So in order to solve this problem, I had to create a PI controller algorithm using Python. And the function of this controller is basically to compare the balance stress with the target stress. And if those two are different, then it applies a new compensated or corrected field until those two stresses are equal. Now, this is also a work in progress, but here you can see the effect that different residual stress fields have on the stress intensity factor of the crack. There are two different load cases, 32 and 46 kilonewton. And for each load case, the defect was surrounded by different stress fields. So there's a case with no residual stress fields applied, which is the one in black. And then there's cases going from 100 to 300 megapascal peak compressive stress. And as expected, the bigger the compressive residual stress field is, the smaller the stress intensity factor will be. However, you can see that for these particular two cases, the delta K is still much more high than the delta K threshold, which is around 2 for this alloy, which basically means that the cracks are still likely to initiate and propagate for these two load cases under those specific stress fields. So basically, once this model is finished, I'll be able to understand what residual stress fields I should try to achieve with the peening treatment in real life in order to improve or to get the most benefits and life improvement for this type of joints with this type of defect. So to wrap up all of that information, the main conclusion that I wanted to share is that so far this project has allowed me to conclude that the failure in a friction stir welded joints will be a competition between three main factors. The first one being the stress intensity factor at the defect tip, which is variable along the length and also depends on the geometry of the defect. Secondly is the microstructure of the material. And finally, and probably the most important, the residual stresses, both the residual stresses that come from the welding process alone and the residual stresses that come from the peening treatment, which will superimpose with those initial residual stresses. And that's basically it. Thank you very much for listening to this presentation. I don't know if we have any time for questions, but if you need to discuss peening and friction stir welding in the future, just feel free to drop me an email at my Cranfield address. And thank you very much.
Thank you so much, Joanna. We really appreciate that talk. We do have one question that came in. We have time to answer it. The question is, for those not familiar with FSW, can you review the lack of penetration terminology, please? Okay,
yeah. So a lack of penetration defect is very similar to what's traditionally called as a lack of fusion defect in welding, but it can't be called a lack of fusion defect because, as I said, there's technically no fusion in the process. So if you think about two plates being joined together and you have the tool rotating on the top, the friction from the rotating tool will generate quite some heat input, and that energy essentially needs to travel throughout the whole thickness of the material. If it doesn't do so accordingly, which depends on the friction stir welding parameters, then you will have an incomplete bonding of the two plates on the opposite side of the tool, which is the root side, as I said. So that's essentially what a lack of penetration defect is.